We're going to talk about what happens to an integral when you change coordinates. How do you accommodate this change of coordinates? What do you have to do to the integral to make all this work correctly? Okay, so let me just give you a couple very simple examples of changing coordinates, and then we'll talk about things in more generality. Okay, so let's look at a integral from single variable calculus, something like this. All right, we want to do something to make, we want to change coordinates to make this integral easier to do, and this is called U substitution, or just the substitution method. You don't have to use the letter U. But I'll use the letter U here. Let's let U equal x squared plus 1, and then we know that du is equal to 2x dx, which tells us that the x dx is actually equal to, just divide both sides by 2, it's 1/2 du. Okay, so I can go back to the original problem and say that, well, okay, well, if x squared plus 1 is u, I can just replace all this with u. And then x dx, this part over here, is the same as 1/2 du. So this whole integral just becomes the square root of u, and then x dx is 1/2 du. All right, so in this change of variables, we've taken an integral which looks somewhat complicated and turned it into something much simpler. Okay, and then you could go through and finish resolving this integral, simplifying it, and evaluating the integral. Let me give another example where we use polar coordinates. Okay, so let's imagine that we have an integral e to the minus x squared minus y squared dA. And I want to go even further with this and describe what region we're integrating over. Okay, so we're going to integrate over a region R. All right, so I'm going to describe this region just with a picture. Okay, so let's draw this picture down here. We'll just integrate over the upper right corner of a unit circle. Okay, so this is 1, this is 1, this is unit circle, and inside that is R. Okay, well, how would we set this up? Well, the trick to doing this type of integral here is actually to use polar coordinates, and that's suggested by the shape of the region we're integrating over as well. So polar coordinates says that x is equal to r cosine theta and y is equal to r sine theta. And from that we know, using some trig, if you just take x squared and add y squared, you'll see you get r squared. Furthermore, we know that when we convert to polar coordinates, dA is equal to r dr d theta. And that's something that we learned when we talked about polar coordinates. Okay, so if I want to transform this integral into polar coordinates, what I'll do is I'll replace the minus x squared minus y squared. Well, that's the same thing as minus r squared. So this becomes e to the minus r squared. And dA becomes r dr d theta. And then the bounds of our integral we can even figure out. R ranges from 0 to 1, right? If I go from 0 all the way out to 1 is when I hit the end of the unit circle. So that R goes from 0 to 1, and theta goes from 0 to pi over 2. And so that specifies this integral in polar coordinates. So we've changed from Cartesian coordinates here, where we might have dx dy, and we changed to polar coordinates where we have dr d theta. Okay? So in both of these examples, something happened when we changed coordinates. When we changed from dx to du, notice that some other variables got changed along the way. Where we had an x, it now became 1/2. In some sense, you could think that we multiplied by 1 over 2x to get from here to here. And over here, like I said, dA can be thought of as dx dy, right? And it changed to dr d theta. But it didn't just change exactly to dr d theta. there's a guy here that got thrown in. It's not just dx dy becomes dr d theta, it's like dx dy becomes r dr d theta. So changing coordinates is a little bit more sophisticated than just changing the variables that are used. We have to think about these other things that happen. And this other thing that gets introduced is called the Jacobian. And that's something that we need to talk about if we're going to be successful at changing coordinates when we use more abstract coordinates, more general coordinates. Okay, so what we're going to look at is we're going to look at what happens when we just change a small little rectangle from one set of coordinates to another set of coordinates. And I'm going to stick with the example of polar coordinates here. All right, so suppose that we have in polar coordinates, although this could be any coordinate system, I'm going to specify a rectangle from r1 to r2 and from theta 1 to theta 2. Right there it is, a little rectangle. And I'm going to transform this into Cartesian coordinates, or it could be any coordinate system, but let's imagine Cartesian coordinates for this particular example. All right, and see what this becomes. Okay, so if this was polar and this was Cartesian, well, if r changes, that means I'm changing my radial distance from the origin. So going from here to here is like going from here to here. All right? And then going from here to here, going up, changing theta, is moving along a circle, right? Because theta is an angle. So it's like moving from here to here. And what we end up getting here is a wedge shape. All right, so this rectangle became a wedge in polar coordinates. What I want to do is see how the area of this rectangle changed as we moved to this wedge. The change in the area, that's the factor we have to multiply the dA by in the integral to accommodate this change of coordinates. That's going to be the Jacobian, the thing that we have to introduce when we change coordinates. How can we get an idea of how the area changed? Well, what we can do is we can look at the area in this picture. And what I'm going to do is I'm going to think of the function that took us from one coordinate system to the other one. I'm going to call that f. Okay? And if I think about what happened when I moved from here to here, well, theta 1 is fixed and the r is changing. All right? So you see this point right here, this is just the f of r1 theta 1. That's what got me here. And as I move along this, I'm changing my r. So this line segment here is f of r comma theta 1. Theta is fixed. It's equal to theta 1 the whole time, same angle, but the r is changing. And this curve here the r is fixed. I'm staying on the same arc, but the theta is changing. So r is fixed at r1, but theta is a variable that's changing. So to approximate the area of this thing, what I'm going to do is create a vector that goes from here to here. All right, and I'm going to think about what that vector might be. Okay, well, what we're going to do is we're going to actually think about derivatives here. So let's just look at the derivative, the r derivative of f. If I differentiate f with respect to r, what happens? Well, we know that the definition is that it's the limit as a small change in r goes to 0. And then we do a difference quotient where we just wiggle the r coordinate just a little bit by delta r. So we're just going to add delta r to the r coordinate. And then we're going to look at the difference between that and where we started. So we started here, we changed r a little bit, and we ended up here. And this is the difference between those 2 points. So that's a vector. That's this vector. Right? The derivative is what you get when you divide that by how much you changed by, so by the delta r. And then you take the limit as delta r goes to 0. Now, that's exactly what the derivative is. Now, if I take the limit off, and as long as I have delta r small, so this is the limit as delta r goes to 0. If delta r is approximately equal to 0, then this is approximately equal to this. Okay? And then I can multiply both sides by delta r. So I'm going to take this stuff in the numerator and write it down. And then I'm going to multiply both sides of this by delta r. So this is what happens when I wiggle the r. I just changed r a little bit, and I'm saying the difference between this and this, so this vector right here, that's what this is approximately the r derivative of f times delta r. And you can do the same thing for theta. Just think about the vector that goes from here to here. That's what you get by perturbing the theta. So we do the same kind of thing, but we do the theta derivative. And so what we'd get is, remember what we're after here. We want to find how the area of this rectangle changed when we changed it to this wedge. Okay, so we want to approximate the area of this wedge. All right, and the area of the wedge is going to be, if I think of the vector that takes me from here to here and the vector that takes me from here to here, I just need to find the area of the parallelogram that's spanned by those vectors. And that's approximately the area of this wedge. Okay, how do you get the area of a parallelogram? Well, if you remember, when we talked about cross product, there was a formula relating cross product to the area of a parallelogram. And you might say, well, wait a minute, we can't use cross product because this is all in 2 dimensions. But you actually can if you imagine a third dimension's coming out, and just imagine that these vectors, so say there's a z direction here, but these vectors just have z component 0. So they're the same vectors, they have z component 0, and now they are 3-dimensional vectors, and we can take their cross product. So viewing these as 3-dimensional vectors with z coordinates 0, we know that when we take their cross product and take the magnitude of that, we end up with the area of this parallelogram. So the area of the parallelogram here, or the area of the wedge, is approximately equal to the area of the parallelogram. So it's approximately equal to this vector cross the magnitude of this vector across this vector. But we said that this vector, that's this, it's approximately equal to this. So what we want to do is we want to take FR, delta R, right, and cross it with F theta, delta theta. That's this vector here. And then take the magnitude. All right. Well, delta theta and delta r and delta theta, these are just numbers, so you can pull these out. All right. The FR and F theta, these are vectors. Okay. So what I can say here, this is FR cross F theta, delta r, delta theta. How do we compute FR? How do we compute this cross product? We have to think more about how to represent F. Okay, let's look at the picture. F is a function that takes r and theta, any point r theta, and transforms it into a point x, y, right? So when we write down f of r theta, we get a new point. Its x-coordinate depends on r and theta, and its y component coordinate depends on r and theta. So we get an x, in the end we'll get an x and a y, but each x and each y they're functions of r and theta, right? So the function f really depends on 2 other functions, the x function and the y function. So we put in 2 coordinates, and then in the end we get out 2 coordinates, okay? So what is FR? FR is the r derivative of this business, right? So that is we differentiate this stuff with respect to r. So we're going to have the vector that's x differentiated with respect to r, y differentiated with respect to r. And remember, we're actually going to think of FR as a 3-dimensional vector. I mean, really, I should just end it right here. But if we're going to take the cross product, we need to think of it as a 3-dimensional vector. So we're going to add a 3rd component. Maybe I could have done that up here, said this is a point whose 3rd component is 0. If you want to think about it that way too, that's fine. All right, make the change up here before we get to here. That's fine too. And then f theta. Well, that's what I get when I just differentiate these with respect to theta. So I'm going to have x theta and y theta and 0. And what do I need to do with these? I need to take their cross product. Okay? So what is FR cross F theta? Well, that is the determinant of this. There's a way to do it. This is a trick for doing the determinant. You can write things down this way. So I'm going to write down this vector, my FR vector. And then I'm going to write down my F theta vector. And then I'm going to take the determinant here. All right, so the I component is going to be the determinant of this. So it's this times this minus this times this. Well, that's 0. So it has no I component. These are the unit vectors, remember. What about the j component? Well, now I take xr times 0 minus 0 times x theta. And actually take the negative of that. But it doesn't matter because it's 0. So I get 0j component. And then what happens when I go to the k component? I get xr y theta minus x theta yr. Okay, that's not 0. Not necessarily. xr y theta minus x theta yr. And that's the k component. So I get a vector 0, 0, this. This. Now, what we want to do is we want to take the magnitude of this, all right? So the magnitude, because that's what we were after up here, all right? So the magnitude of this thing, well, look at it. It's a vector 0, 0, and then a multiple of the k vector. So it's just pointing out in the z direction this amount. So the magnitude is just the size of this. It's just the absolute value of this quantity. So the magnitude is xr y theta minus x theta yr, absolute values. That's the magnitude of that vector. Okay? And so, putting this all together, the area of the wedge is that thing multiplied by delta r delta theta. So the area of the wedge is approximately equal to delta r delta theta. What we say is, when we're converting coordinates, if we want to find dA, the area of a small little piece, and d means infinitesimally small. So that's when, after we take that limit, if we imagined we put this limit back, all right? So all the delta r's become dr's. That's the notation we use, and a small area becomes dA, right? So dA ends up becoming, when you, I'm washing over the analytical details here, but this is what happens. This becomes dr d theta. Now guess what happens when you convert to polar coordinates? Well, you might know from polar coordinates what this is going to become. Actually, let's go ahead and do that as an example, okay? Maybe we can do it right here because we got the picture. In polar coordinates, what we know these functions r and y, right? You know that in polar coordinates, x equals r cosine theta and y equals r sine theta. So we've got our x function and our y function in terms of r and theta. That's what these are. So if I want to find the dA, I need to find xr, I need to find x theta, I need to find yr, and I need to find y theta. Okay? Well, xr is just the derivative of this with respect to r. That's just cosine theta. X theta is the derivative of this with respect to theta. That's minus r sine theta. Yr is the derivative of this with respect to r, so that's sine theta. And y theta is r cosine theta. Now remember what dA was. What dA became, it was the xr y theta minus x theta yr, and then we had the dr d theta down here, dr d theta. Well, what is this stuff? Well, it's xr times y theta, so that's r cosine squared theta. I'm going to have to go to another, maybe we can put it down here. So dA is going to become xry theta. Well, that was r cosine squared theta. When I multiply those together, right, I get r cosine squared theta. And then what about x theta yr? Well, x theta times yr is minus r sine squared theta. But I'm subtracting it, so I get plus r sine squared theta. Dr d theta. Okay. But this, the r factors are out, and cosine squared plus sine squared is 1. So what we really get is just r. So we get r dr d theta. So that is why in polar coordinates, dA is r dr d theta. This guy right here is called the Jacobian. Oops, went off the screen. That's the Jacobian. That's this. This guy right here is the Jacobian. And the Jacobian is nothing more than the determinant of this matrix right here. The absolute value of the determinant. So you take this times this minus this times this. That's the Jacobian. Okay, so that's how we change coordinates.